Good day, everyone. So we are now in third week lesson in general mathematics, and our topic for today is about rational functions. And the objectives of this lesson is you will be able to distinguish as rational function, rational equation, and rational inequality. Also, solve the domain of rational functions and organize solutions involving the domain of rational functions. Okay, so our topic for today is about rational functions. And before we formally begin discussing rational functions, let us discuss first some basic properties of equality. So we have here the reflexive property, which means that x equals x. So it states that a number is always equal by itself. For example, we have 5 is equal to 5. So a number will always be equal to itself. We have the symmetric property: if x equals y, then y equals x. So let's say we have 1 plus 6. Okay, so I will write it down for you. So let's say we have 1 plus 6 is equal to 7. The same also saying that 7 is equal to 6 plus 1. Okay, so I'm sorry, my mouse is not in good condition. Okay, so we have 6 plus 1. Next, we have here the transitive property. So it states that if x equals y and y equals z, then x equals z. We have addition property. So if you're given x equals y, in your addition property, we are adding the same number to both sides of the equation. So let's say we add z to the left side, we need to add uh, z also on the right side of the equation. So for the subtraction property, that is subtracting both sides of the equation by the same number, and your multiplication property is multiplying the same numbers to both sides of the equation. And then we have division property, that is dividing the same numbers to the both sides of the equation. And lastly, we have the substitution property. Okay, so in your substitution property, we're just replacing the value of a certain variable if it is given. Okay, so we have here the definition of your rational functions. If p of x and q of x are polynomials with no common factor, and f of x equals P of x all over q of x, for q of x is not equal to 0, then f of x is called a rational function. So take a look in your numerator, that is p of x, which means our numerator must be a polynomial function, and also your q of x must be a polynomial function, so that f of x can be called a rational functions. So your q of x must not be equal to 0, because it will make your function undefined. Okay, so we recall the concept of polynomial function. P of x, a polynomial of degree n, is of the form p of x equals, so that is your a sub n x exponent n plus a sub n minus y x exponent n minus 1 until a sub 0. So your a sub 0 there is a constant, where a sub n must not be equal to 0. Okay, and where your a sub I is a real number for all I equals 1, 1, 2, 3 until to the n terms. Okay, so we have here terms, that is the components of your rational functions. Okay, so you're given p of x equals 6x exponent of 5 minus 8x cubed plus 2x. So we have here three terms. The first term is 6x exponent of 5. Our second term is negative 8x cubed. Our third term is 2x, and we call these terms. And when we say leading term, it has the highest degree of exponent. So we have here, since the variable x here has the highest degree of exponent 5, so 6 is our leading term. So we can find our leading term here. So you base it on the highest degree of exponent. Okay, so we have here example of polynomial functions. P of x equals 3x cubed plus x squared minus 16x plus 2. So this is an example of polynomial functions. So look at their exponents, which is a positive whole number, therefore it is a polynomial functions. Let's say f of x equals 15x exponent of 4 minus 5x cubed plus 3x squared plus 8x plus 3. Now let's take a look at with their exponent. If it is a positive whole number, then therefore it is a polynomial function. Okay, so let us check. So the exponent here is positive 4, the exponent is positive 3, and the exponent here is positive 2 and positive 1. So therefore, f of x is an example of polynomial functions. Okay, so how about g of x? So g of x equals 2x exponent of 1 half minus 18x plus 2. Okay, so this is not a polynomial function because the exponent 1 half is not a whole number. So it must be a positive whole number to tell that it is a polynomial function. Okay, so take note, 1 half is a rational number. So it has a fraction and it is not a whole number, so therefore it is not a polynomial function. Okay, so let's say the domain of the rational function is the set of real numbers except for the x values, which will make q of x equals 0. Okay, so when we say domain, these are the possible values of your x that can be found in our x-intercepts, but if we substitute that value or that x values to our denominator and will make q of x equals 0, then that x value should not be part of your domain because it will make our functions undefined. Okay, so we have here examples. Find the domain of each rational function. So we have letter A, f of x equals 1 all over x plus 2. So for the solution, to find the domain is to equate the denominator equal to 0. So we copy x plus 2, then we equate this to 0 equals 0. And then solve for x. So to remove a positive 2 here, we subtract 2 to both sides of the equation. So we have now x equals negative 2. Okay, so therefore, the domain of f is the set of real numbers except negative 2. Because when you substitute negative 2, it will make q of x or our denominator 0. Okay, so I have here negative 2 plus 2. So that becomes 0. So therefore, it will make my q of x 0 and negative 2 is not part of the domain. Okay, so I hope you understand in this part. Okay, letter B, let's say f of x equals 2x plus 3 all over 3x minus 9, and solution is to equate the denominator equal to 0. So you copy 3x minus 9 equals 0. Then we need to remove 9 here on the left side of the equation since we are solving for x. So we add both sides by 9, that is applying addition property of equality, and we have now 3x equals 9, and then we need to remove the coefficient 3 here in the variable x because we need to solve for x. So 3, we divide both sides by 3, and we have now 3x divided by 3 equals 9/3, and simplifying we have x equals 3. Okay, so therefore the domain is the set of real numbers except 3. Okay, you can take all the values of x except for positive 3 because when you substitute 3 here in our equation, it will make q of x equals 0. Equal minus 9. So 3 times 3, that is 9. So 9 minus 9, that is 0. Okay, let's move on. Okay, so let's have here another example. So given f of x equals 1 all over x squared minus 4, so we equate the denominator equal to 0, x squared minus 4 equals 0. So take note, this is a difference of two squares, so we can change this in the form of quantity x minus 2 times the quantity of x plus 2 equals 0, so that is applying factoring, and we have now, we equate x minus 2 equals 0, and we equate also x plus 2 equals 0. And solving for x, we have now the solution, x equals 2 and x equals negative 2. So we can also solve in this way. So we have, we equate the denominator equal to 0, x squared minus 4 equals 0, then adding both sides 4 to remove negative 4, and then we take, the remaining is x squared equals 4, and then we take the square root, so we have now x equals the positive negative 2. Okay, so the domain of f is the set of real numbers except 2 and negative 2. So I have here illustrations showing the graph of rational functions in real life. So a road is an example of a rational functions. Okay, so in next week we will be discussing about asymptotes and other parts of your rational functions. Okay, so for your activity is tell whether the given function is a rational function or not. Then you write RT if it is rational function and NT if not. Okay, so you have your assignment. Kindly write your answers on a one whole pad paper so you can combine there the activity, assessment, and assignment in on a one whole pad paper. Okay, so that's all for today. I hope you learned something. If you have questions, kindly message me to our group chat, and thank you for listening.